This is Lesson 4, Unit 11 Buffers, calculating the pH after adding OH minus to a weak acid, and we'll be using the equation pH equals pKa plus log A minus over HA. So let's take a look at adding a strong base to a weak acid right here. And notice that as we go through this process, we are creating a conjugate acid-base pair. So we have a buffer pair that we are forming here. Hence, as we add the sodium hydroxide, we are making a buffer. Likewise, here we have a weak base being titrated by the strong acid HCl, and we are forming another buffer pair. So what I'm going to go through is the calculations for both types of systems. First we'll titrate or add sodium hydroxide to acetic acid, and then we will add hydrochloric acid to ammonia. So here's the question: what is the pH of a buffered solution made by dissolving 0.45 moles of weak acid, HA, and 0.1 moles of KOH into 650 mLs of solution? If we look at our reaction, we are going to be making HA plus OH minus, and because this is a strong base, it's going to go 100% to making the conjugate base and water. So this is a limiting reagent problem, which means that we will start it with a BCA table, before, change, and after. So let's go ahead and label this B, C, and A. Remember, this stands before, change, and after. And because it's limiting reagent, we're going to have to make sure that we have everything in moles. And in this case, it has been very conveniently given to us in moles. We have 0.45 moles of HA and 0.10 moles of OH minus. So initially we pretend that no A minus has formed yet. This is a 1-to-1 ratio. The hydroxide is our limiting reagent, so that will be completely consumed, and will consume a matching amount of HA and produce 0.10 moles of A minus. Then we calculate our after concentration. 0.45 minus 0.1 is 0.35. We have none of the sodium hydroxide left, and we have 0.10 moles of the A minus. So if we look, we have just created the components that we need for a buffer. So we use our equation that pH equals pKa plus log A minus over HA. We need our value for pKa, and that is going to be the negative log of 3.5 times 10 to the negative 6th, or 5.46. Remember, our sig figs are only the numbers after the mantissa. So we plug in. pH equals 5.46 plus the log of 0.10, our A minus, over 0.35. And we solve, and that is 4.92. So as we look at this, we've made a buffer for pH of 4.92, but let's see which one it will buffer better against. Will it buffer better against adding hydroxide or better against adding base? So if we look, we have a higher ratio of the HA, so this has a higher capacity to buffer against base if we continued with just this solution. So a higher capacity to absorb base. Likewise, it has a lower capacity to absorb acid. Let's look at a second problem that looks at the pH of a buffer solution made by dissolving 0.10 moles of the HCl and 0.3 moles of the NH3. Again, we're going to set this up as a BCA table. So we're going to have NH3 plus HCl, 100%. We are going to be making NH4 plus, and we have BCA. Our ammonia is 0.30. HCl is 0.1 mole. This time the HCl is our limiting reagent, so we have minus 0.10, minus 0.10, plus 0.10, and then when we do the math, our final concentrations after the reaction has gone to completion, 0.20 for the NH3 and 0.10 for the NH4. This is our HA, this is our A minus. So we're going to have pH equals pKa plus log 0.20 over 0.10. We need to calculate the Kb, change Kb to pKa. So we're going to have the negative log of 1.8 times 10 to the negative fifth. After that, after we go through some conversions, we're going to have that pKa is equal to 9.25. So pH is going to be equal to 9.25 plus log 0.20 over 0.10, or 9.55. Okay, I'm going to come back to this calculation up here because I realized I kind of leaped ahead. So I've redone some things here. Negative log 1.8 times 10 to the negative fifth is your value for Kb. So therefore, pKb is going to be equal to 4.74. pKa is going to be 9.26. Then we substitute that in and we have pH equals 9.26 plus log 0.2 divided by 0.1, or 9.56. The last problem we're going to do is to take a look at what happens when we add an excess of a strong acid to a weak base. And basically we're proving that this is not a buffer when you have an excess of either the strong acid or the strong base. So let's set up the BCA table again. So we have NH3 plus HCl, and remember this reaction is going to go 100%. And we're going to make NH4 plus Cl minus, which we really don't care about. We have our B, C, and our A. The ammonia is 0.10, hydrochloric acid 0.30, nothing to begin with. Now our ammonia is our limiting reagent. So we're going to be adding 0.010, and our final concentrations are no ammonia is left. We have 0.20 moles of HCl and 0.10 moles of the ammonium ion. So when we look, it is not a conjugate acid-base pair. Weak acid-base pair. And what's going to dominate the pH is going to be our excess HCl. So excess HCl will dominate the pH. And what we'd end up doing is simply taking our moles of HCl that are left and dividing it by whatever our volume is. Okay, so whatever the volume, so whatever the liters, to find the molarity of H+. So definitely not a buffer system when we have an excess of a strong acid. And the same would hold true if we added a strong excess of strong base to a weak acid.